Here we are going to take a look at one interesting principle from geometry called as Cavalieries principle, and it gives us a very powerful technique of figuring areas and even volumes of certain shapes and solids. So the principle goes something like this, that if you are given two shapes, in our case say these two triangles, Cavalieri calls them regions, and if they are bound between two parallel lines, so here are the two parallel lines, say L1 and L2, and if you draw a third parallel line like this, which intercepts these two regions, and if the intercepts, I have indicated them with these yellow segments, happen to be of the same length, not only for one position of the line, but for every other position. Say here they are both 100, here they are both 75, here they are both 50, here they are going down to say 25, or in any other position, they are always equal. So if that happens, then these two shapes will necessarily have the same area. Now, after a little thought, this might look very obvious to you. Okay, nothing impressive. But when you look at the application, then you will be impressed. So let us see an example. Let us start by considering a line. I'll call it the ground, and a circle on it. I will call it a wheel. And then we'll be setting this wheel in motion. So it will be rolling on the ground without slip. And we are going to consider a point on that circle, let us say this point, and trace the path it traces as it rolls. You know this path is called as the cycloid. So here we have a cycloid being generated, and we are going to do it one more time with an identical circle. But this time, instead of taking the ground as our support, we'll be taking the ceiling as our support. Okay? So we'll be taking an identical circle that will roll on the ceiling. But then the circle will be going in the counterclockwise manner. So this is a kind of motion we'll be getting that time. So it is going counterclockwise, and like before, we are going to trace the path here. Here we go. So this path again, although it looks somewhat different, is again a cycloid. It will have the same properties, only it is kind of inverted upside down and shifted a bit, but it is still the identical cycloid. Now suppose we take both these circles, one on the ground, other on the ceiling, and set them in motion simultaneously. Then this is how they will move. Say these two yellow radii, they start from the same position, but because they are rolling in opposite directions, clockwise and counterclockwise, they will diverge like this. And while doing so, they will be tracing these two cycloids. So you can see they again meet at the top point, and again the two radii diverge, tracing these cycloids. And we are now challenged to find out what is the area enclosed between these two cycloids. Say this petal-like shape that you see here, we are asked to find what is the area there. And that is where Cavalieris principle helps us. Now to apply Cavalieris principle, I'm going to introduce one more geometric element in our figure, and that is the cross section of the circle. So here I'm going to connect these 2 points, okay, the end points of these two radii by a straight line. So this segment here will always remain horizontal because of symmetry, because the radii are moving so, and therefore it is parallel to these two lines, the ceiling and the ground. So what is this line doing, this chord doing? It is nothing but a cross section of this region or shape or circle. But this is a very special cross section. Look at its end points. What are these end points doing? They are the tracing points of the cycloid. So this point will lie on one cycloid and this would lie on the other. So let us show the curves and trace the whole thing together. So let's start moving these two circles. And now you can see this cross section here is not only a horizontal cross section of this circle, but it is also the horizontal cross section of the petal. So now the circle and this petal share a identical cross section, and therefore the two must have the same area. So what is the area of this petal? It is nothing but the area of this circle. This is really a very beautiful and profound result, and Cavalier's principle helped us reach there. So let us once again sum up the things. Here we have been given two shapes or regions. One is this circle, one is this petal-like shape bound by these two cycloids. And both these shapes are bound between two parallel lines. One is the ground, one is the ceiling. And if we take a third line parallel to these two, so a horizontal line, then every such horizontal line has the same cross section of these two shapes. So this chord of the circle and horizontal chord of this petal, they are always identical. And therefore, according to Cavalieris principle, they must have the same area. So let us fill up those areas as we go, and then we will see it a little better like this. So as we go, as we move this chord up, we are filling up the circle and we are also filling up the petal, and those two areas are equal all the time. So when we complete this, the entire petal and the circle will have the same area. So let's run it back and forward. So at any given point of time, the areas marked by this green fill are equal. A remarkable result. In the next video, we'll be applying Cavalier's theorem not to two-dimensional but three-dimensional figures. And there we'll be dealing with not areas but volumes instead. And I promise you the result is going to be just as impressive. Take care.